Hello, everybody. My name is Francisco Weber. I'm the founder and CEO of Cortical.io, which is a natural language understanding company operating out of Vienna. And I will talk today about a concept that we try to bring in the domain of natural language understanding, basically, which is semantic supercomputing. And I will try to explain what that means. So, of course, we all know the problem that the amount of data is absolutely exploding currently. What we can also observe, if we look at how the data unfolds as it comes in, is that the part which I would consider to be the human-generated data, which very often is text precisely, is a massive part of that data explosion, and we do actually have to handle this. The problem is that, in fact, data gets more and more, but our current computing platforms, if you want, our computers, based on a architecture that we keep using, the von Neumann architecture, of course, comes now to sort of an end in the sense that it's very hard to improve throughput and processing performance and things like that, which, of course, by adding the two together, getting more data and not getting faster, decreases productivity, of course. So I will try to sketch the technical perspective to that problem and our proposal on how to solve this. Of course, we have to look first to the actual von Neumann computing architecture. Then we have to see how we are currently trying to tackle that amount of data that is coming in by using machine learning, mainly what I now would call statistical machine learning. And then I will switch over and present the way how we think which would be a good way forward, which is semantic folding, which in fact then leads to the semantic supercomputing concept. So the von Neumann computing basically is, as you probably all know, architectured in a way that we have the memory on one side and we have on the other side the processor that's supposed to make calculations based on the content of that memory. The problem is, of course, that the link between the processor and the memory is of a defined size. So the more data we want to basically pipe through this, we get sort of a traffic jam on the bus, which is actually the structure that links the two. So that seems to be sort of a systematic bottleneck on how to improve computational performance. If we go to the next layer, beyond the actual processing layer, to the way how we want to actually process the data. So we have this model of machine learning that we use, where we basically take a set of training data, we derive a model from that, which is supposed to behave specific to a use case, and we try to process that data as it comes in general terms, to transform it into an output stream of the data. And here again, we do see a number of bottlenecks coming in. So first of all, there is the bottleneck to, in the first place, find the right set of data for a use case and to provide enough data from there. Then we have, of course, this first phase where we do the training, which is typically an offline phase and where we create a model based on that. And that model, of course, has then limitations in terms of size, in terms of time it takes to process through that model, and so on. So plenty of bottlenecks, basically, that we have to face. And the main problem, it seems, within this universe of statistical machine learning is in fact efficiency. Because on one hand, it seems that what we expect to provide a system with features of a specific use case, with examples of what value those features can take, and to derive a model from this, is basically depending on speed and amount of data, which all comes down to efficiency. I will try to show this with a number of aspects. So one aspect will be the findability issue. So how can I access the data that I need to process properly? Then, of course, the Neumann Gap, the problem that we cannot keep up with the processing power as our models grow larger, and derived from that, of course, that we need more and more power, because the only way we can actually improve the amount of data that is processed is by adding more and more computational units. And then in the end, of course, we have to do something with the myriad of models that we keep generating on all of our use cases. So the findability issue is quite an interesting aspect, which sort of came in already a while ago and has been investigated by people in the information retrieval domain. And what they found is that, interestingly, if we use statistical modeling, which basically in the context of a search engine comes to sort of counting words to sort of reduce it to a minimum, and inferring the relevance of a document based on the number of times certain words occur in the document, what they could find out is, in fact, that as soon as the collection of data that we want to actually index for searching goes beyond a certain size, we have the effect that regardless what kind of query we could cast to the search engine, we will not find all the relevant documents. And so one of the conclusions of the paper actually is that in certain systems that are out there in production, they have made experiments showing that they can take away up to 80% of the data without the user actually noticing it. And this is because there are more and more documents as the collection grows, where you can cast whatever query and you will never actually find them. Then, of course, bringing up the Neumann Gap, how I call it, which basically just represents the gap that keeps growing between the power of processing that we can afford and the amount of data that increases. And that leads to, foremost, an energy problem. So interestingly, we are all talking about sustainable mechanisms and improving the current state of CO2 emissions and things like this. And all the industries are actually trying hard to reduce their power consumption and to make their production mechanisms and processes more efficient. And the only industry that seems to go exactly the other way around is the IT industry. Let me put it like this. So interestingly, we might not always be aware of it, but we already currently use as much energy for our computational needs as we use energy for the global air traffic that we have. And if we continue growing in the pace we did over the last years, in 2030, we will actually use as much energy for IT as we do for all the cars on the planet. So this seems to be a major part of the energy consumption. And I think it would be very important to find a way of developing more efficient ways of doing machine learning. Something like high efficiency AI would definitely be sort of in big need for the current situation. So the last aspect I want to talk about here in terms of the statistical modeling problems is that all the models that we create by providing examples of certain use cases that we then use to sort of infer a model from it will be a model that is only applicable to this very use case. So if we extrapolate that trend and we end up in a society where every little classifier that is used in some business AI application needs its own model, we have the problem, or we will have the massive problem that we will have to live in a universe full of different models, and the management of the models can by itself become overwhelming. So as a result from these shortcomings of the way how we currently try to approach those issues, sort of the technology impact that this statistical modeling has is, of course, as I said, the findability issue, which can actually lead to, in the maximum effect, I would say, to something like fake news. So if truth is not easy to find, or possibly you don't find it at all, it's very easy to cast any sort of wrong information without making it easy to be proven wrong. Then we have the climate issue, the energy issue, which relates to this trend that we have to increase more and more our processing power to keep up with the data that comes in. Doing statistical models in general is sort of optimizing averages between aspects and features. And if we do this on a very large scale and very systematically, we will on one hand, of course, find out certain things that we are looking for, but everything will always converge to some average result, which of course makes it hard to find sometimes the interesting examples which are not part of the average. And that, of course, also leads to problems while trying to sort of treat users of systems on a very averaged model, sort of. We'll treat groups of people sort of in the same way if they have certain aspects in their behavior. And that is, of course, a fundamental mechanism that allows to sort of manipulate, on the quotes, motivate people to behave as you would expect in these average systems. So we try to sort of overcome this by trying to stay away of statistics and trying to find an alternative fundamental approach on doing processing and machine learning of data, specifically of language data, which has the problem on one hand of being data that is not directly usable. It's data that is mainly captured in labels and consists of symbols, sort of. So there is no semantic grounding. So nothing in the word cat actually points to some aspect of what a cat is in reality. And when we try to find sort of a good implementation for that kind of language intelligence, of course, we have to look at the human brain. And that's exactly what we try to do, is we try to learn from how the brain seems to handle these aspects in a general fashion, information aspects, but in a more specific fashion, the way how language is actually processed in the human brain. And interestingly, the human brain does not create statistical counts of words to figure out what they mean, but the brain can only work with actual experiences. So what we do typically when we learn a language is that we store utterances, because we typically learn language before we learn writing. And those utterances basically consist in semantically grounded pieces of language, semantically grounded because we hear or say the word cat very often when we actually see or hear or even feel when we touch it, that cat. And that basically leads to this situation that the words we learn as we learn a language are typically grounded in actual experiences. And what recent neuroscience actually shows us is that if you arrange those experiences in a specific way that sort of handles the representation in a way that it can be processed by neurons, then a lot of things change. And as a consequence, what we did is we created a system that is able, on one hand, to learn what language is, and on the other hand, then based on what it has learned, represent every atom in this language, which would be any word, in what we call a semantic fingerprint. And that semantic fingerprint, you see here, those squares you see are actually semantic fingerprint of phrases. So for example, the phrase signed contract, and on the other hand, you see the phrase done deal. And when you convert both of them into a semantically grounded representation that corresponds to the information representation that we assume to be similar in the brain, what we get are two fingerprints that have a lot of common features. So every dot in my representation is actually a feature within this fingerprint, and each feature points to a specific utterance, if you want, something that has been really perceived. So the only way how the system can sort of figure out how the word works is basically by making analogies between patterns, semantic fingerprints, for example, that come in and compares them, makes an analogy with patterns that have been stored. And as we can show, all the thinking can be represented based on analogies between two representations of language or any other semantic content, means content that has a meaning in the real world. As you see, if you change one of the two utterances to be compared into something completely different, like Star Trek, for example, there is literally no or very little match between the two phrases. You can literally see by looking at the fingerprint that it is structured differently. And what is interesting is that with this distributed representation, where a word is defined by all the explicit occurrences of utterances in the right context of that word, that basically represents a fully sort of comparable way of the content of the language. And the way how we do this is that we start, of course, very similar to natural brains, to actually learn about the language. But there, as we are not counting the language and making statistical inferences on it, but we literally use the actual utterance, what we do is that we take the same learning materials than humans would take. So what we do is, for example, if you want to have a system that understands medical records, let's say, using a statistical learning system, we would actually take, let's say, 5 million of those medical records, and we would create a statistical model out of it. If we use our approach, we take actually learning literature, which is textbooks on medicine, and we would extract actual contexts that we find in those textbooks, and we would take those literal contexts to become basically a dot in our fingerprint. And the meaning of that explicit context is captured geometrically. So depending on what words are used in a specific utterance that represents a certain context, the machine learning algorithm puts it on different positions within my fingerprint. So in that implementation, we have fingerprints of 128 times 128. So we have 16,000 possible positions to actually locate a specific context that has been captured. And the sum of those contexts basically represents the semantically grounded representation of a certain word that has been converted into it. So if we look into one fingerprint, if you want, we can actually, behind each of the dots, find the contexts of the reference information that has been positioned there. And what we also observe is that all experiences on the quotes, utterances that talk about similar things end up in similar spaces within the geometry of the fingerprint. So we find here, for example, regions where we have features that contain words like church, altar, baroque for the word organ, but we also see words like liver, heart, and muscle, which are located at a different position because they have a different meaning. If we now take those word fingerprints, whenever it comes to building a sentence, we can create the representation of the sentence by literally converting each component word into its fingerprint and then making a big Boolean OR to basically add those fingerprints together to end up with a fingerprint representation for the whole sentence. And as you can see, a sentence like organs and pianos are musical instruments. We see that the ambiguous part of the word organ, which was referring to body organs, gets sort of thresholded away as no other word in the sentence actually represents this. That fingerprint representation, as it represents the meaning itself, can be sort of independent or is independent from the actual language symbol. So what we see is that for any language that has been learned by the system before, the vocabulary of certain languages, the same words, if you want, in all the different languages render into the same fingerprint. Which makes sense because the word philosophy in English means something very similar to the word filosofía in Spanish, for example. We use now these fingerprints to generate primitives for performing NLU computation. So one primitive very obviously is search. So I can take a collection of text, I can create a fingerprint for each text, and I can allow someone to type in a query, which is again text, of which I generate a fingerprint. And the only thing I need to do then is to order all my document fingerprints in a descending overlap order with my query fingerprint. And I will have immediately not only the relevant documents, but I will have them already in a relevance ordering that makes sense in my context. I can also use fingerprinting to do classification. The advantage here is that I don't need to come up with a lot of examples for each classifier, but I can, in theory, take a fingerprint to classify. So if I want to find out which tweets from the Twitter firehose talk about mobile phones, I can literally take the word mobile phone, convert it into a fingerprint, and compare that filter fingerprint with every incoming tweet, and only above a certain overlap, I can use the message as being a message about mobile phones. I can extract keywords from text by saying this is the fingerprint of my whole text, where I just convert every word into a fingerprint and then aggregate it. And then I can take every individual word and can do with some simple algorithm, I can find out which are the words that contribute most to the text fingerprint representation. And last but not least, I can of course take my fingerprints and I can sort of pipe them as data representation units into more traditional machine learning systems. And what I can observe there is that with much less initial data, basically, I can get my machine learning backend, if you want, to converge faster, simply because the semantic expressivity of my data is much higher. So even a statistical backend sort of needs less examples to learn what the data is about. So with Cortical.io, we have created 3 engines that basically capture that functionality. One engine is a classifier that can also cluster and keyword extract. We have a semantic search system which allows to create a search index, very much like Elasticsearch, with the difference that it doesn't match words, but it matches meanings of words. And then we have an even higher sophisticated application of that base technology with semantic annotation, where we use the understanding of the meaning of the words to locate specific information within documents and extract it. So, for example, like from contracts, which I can show you later. We can, on the other hand, and that's the link to the for Neumann problem that we have, we can use gate array technology from FPGAs, for example, to fully parallelize those bit-driven operators that we do when we do search or when we do classification or when we do a conversion from text into fingerprint. All of that can be close to perfectly parallelized because every feature in my fingerprint representation is actually independent from the surrounding features. So each of them can be calculated in the same time. So we have created a platform that consists of a hardware system, an appliance that contains FPGA elements. And what we do is that we offload the fingerprint calculations of all kinds to the hardware and can achieve substantial improvements in speed. So what you see here is where we basically compare to standard current technology language models out there, like BERT, for example, or Doc2Vec or FastText. And what we can see here is that we achieve easily sort of the same precision than those systems do. The reason for this is that the computation of the models is much faster. So we take about 10,000 times less data to train our models, as we are using the utterances literally, and we have not to create large statistical averages of them. And therefore, we calculate within 2 hours on a laptop a language model that is basically of the quality that you could expect from some other deep learning models available. And because the computation is so fast, we can, of course, refine the system much further. We can have many more refinement cycles, which in the end leads to basically a pretty high precision that we can achieve. So even if an algorithm would in principle achieve a better precision, if that language model computations take very long, you will practically not be able to get it to a certain level. And that's why I keep saying that, in fact, we should not talk about precision of a certain NLU approach, but we should rather talk of efficiency, because only the efficiency allows us to actually make use of the precision that would be available. And as promised, these are just very quick examples on how we apply this in practice. So here we have, for example, for an insurance company, they need to analyze thousands and thousands of insurance offers that their clients got from other insurance companies, and they have to basically see if they can match the offerings and the price from these other offers. That is a very high load activity, which we could actually accelerate substantially by using our technology and locating the key information in the offers to make them comparable in a simple Excel sheet. Another example is from one of the big four accounting firms who wanted to analyze lease contracts because there have been some changes from the financial regulators on the world towards those lease contracts, and so they needed to extract lots of information like termination clauses and things that keep being formulated in a very different way in each contract. And based on our system, they were able to extract, for example, all the termination clauses and compare them and see where they need to put the fix. And the last one is basically similar for a large bank that needed to work of many thousands of ISTA documents, which are financial instruments, and we could help them to reduce their manual labor in extracting that information by literally 80%, which at that scale makes, of course, a big difference. So I've shown you sort of rather specific applications to demonstrate that even very complex solutions can be implemented, but we have successfully implemented use cases in those many areas of business, and you see that they are very fundamentally different. The truth is that basically any large company that has a lot of textual data to handle has to sort of accelerate this by using machine learning. And it doesn't stop there. We are doing this currently with language data, but any data that has meaning has semantics. And so I think as we develop semantic folding, our approach further, we will see that we can also step in the area of machine-generated data or transactional data, because there is a lot of semantics too that can be represented using fingerprints. That would be it from my side.